Have you ever looked inside an old kettle and seen that hard, chalky, crusty layer on the inside? It's a pain to clean, right? Now imagine that kettle is the size of a building, a massive industrial boiler worth millions of dollars. That same crusty layer can form inside it, and when it does, it doesn't just become a pain to clean, it becomes incredibly dangerous. Hello, engineering students, and welcome back. In our last video, we covered the basics of hard water. Today, we're going to explore why engineers are so obsessed with treating it by looking at the 4 major problems it causes inside industrial boilers. First, we'll talk about scale and sludge, the 2 evil twins of boiler deposits. Then, we'll look at a process called priming and foaming, where the steam itself gets contaminated. And finally, we'll briefly touch on a dangerous condition called caustic embrittlement. By the end of this video, you'll understand exactly why hard water is a boiler's worst enemy. Let's get started. Let's begin with the formal definition. Scale is a hard, adherent, and stubborn crust formed on the inner surfaces of a boiler, which are in direct contact with water. It is primarily caused by the decomposition of bicarbonate salts at high temperatures. For example, when calcium bicarbonate is heated, it breaks down into calcium carbonate, which is basically limestone, and that's what sticks to the boiler walls. In simple terms, scale is like boiler cholesterol. It's that hard, crusty layer from our kettle analogy. The biggest problem with scale is that it's a fantastic insulator. It's like wrapping a thick blanket around the boiler's heating surfaces. You have to burn way more fuel on the outside just to get the same amount of heat to the water on the inside. It's an enormous waste of energy and money. Imagine a cross-section of a clean, new boiler pipe. The heat from the furnace transfers easily through the metal to the water. Now, let's see that same pipe after months of using hard water. A thick, white layer of scale has built up on the inside. The heat gets blocked. It can't reach the water effectively. This not only wastes fuel, but also causes the metal of the boiler itself to get dangerously hot. This is a critical concern in every single industry that uses steam. In power plants, scale can reduce efficiency so much that it costs thousands of dollars a day in wasted fuel. Even worse, if a pipe gets completely blocked or overheats due to scale, it can lead to a catastrophic boiler explosion. So scale is the hard, crusty stuff. But it has a softer, messier partner in crime. Let's talk about sludge. Sludge is a soft, loose, and slimy precipitate formed within the boiler water. It is not adherent and settles in areas of the boiler with slower water circulation. It's usually caused by salts like magnesium chloride, calcium chloride, and magnesium sulfate, which have higher solubility in hot water but still precipitate out. If scale is boiler cholesterol, then sludge is like mud in your boiler. It's a soft, gooey sediment that collects at the bottom of the boiler. While it doesn't block heat as badly as scale, it has 2 big problems. First, it's a poor conductor of heat itself, which contributes to inefficiency. Second, and more importantly, this loose mud can get swept into pipes and valves, clogging them up completely and blocking the flow of water. Picture the bottom of a large boiler tank. As the water heats, soft particles start to form and settle at the bottom. Now, an outlet valve at the bottom tries to open. The sludge chokes the system, which can stop the boiler from working or cause a dangerous pressure imbalance. Preventing sludge is crucial for maintaining proper circulation inside a boiler. In chemical factories or food processing plants, a sludge-clogged pipe can bring the entire production line to a halt. Regular blow-down procedures are done to drain this sludge from the bottom of the boiler before it builds up too much. Okay, so we've covered the solid deposits, but hard water can also mess with the steam itself. This brings us to priming and foaming. Let's define these two related terms. Foaming is the formation of persistent foam, or stable bubbles on the surface of the boiler water. Priming is the carrying over of small droplets of water along with the steam as it leaves the boiler. Basically, foaming can lead to priming. Think about boiling a pot of plain water. It bubbles, but the steam coming off is pure. Now, imagine you add a bunch of soap or salt to that water and boil it vigorously. You'll get a thick layer of stable foam on top. As the steam bursts through that foam, it carries tiny droplets of that soapy, salty water with it. That's priming. The steam is no longer pure, it's contaminated with the impurities from the boiler water. This contaminated steam then travels through the pipes. When it cools, the dissolved salts in those water droplets are left behind as hard deposits on pipes and even on turbine blades, causing damage. This is a huge problem in steam turbines used for power generation. The steam must be as pure and dry as possible. If it carries mineral deposits from priming, it can erode or unbalance the delicate turbine blades, leading to very expensive repairs and dangerous failures. Finally, there's one more dangerous effect, which happens under very specific conditions. This is a bit more advanced, but it's important to know. Caustic embrittlement is a type of boiler corrosion caused by a high concentration of sodium carbonate, caustic soda, in the boiler water, which makes the boiler metal brittle. Essentially, in high-pressure boilers, the water can seep into tiny cracks in the metal. The high temperature and presence of caustic soda creates a chemical reaction that makes the steel lose its strength and become brittle, which can cause it to crack and fail without warning. Okay, let's put this all together in a practical scenario you might face. Step 1. Identify the symptoms. The key symptoms are a drop in efficiency and an increase in fuel consumption. This means you are burning more fuel to produce the same amount of steam. This immediately points to a poor heat transfer problem. Step 2. Diagnose the cause. The single most common cause of poor heat transfer in a boiler is scale formation. The water being used is likely hard water, and it has formed an insulating layer inside the boiler tubes. Step 3. List the disadvantages. Based on our diagnosis, the plant is suffering from wastage of fuel, burning more for less heat, decreased efficiency, less steam output, overheating of the boiler metal, which shortens its life, and most importantly, a major safety risk of a potential explosion. Step 4. Propose the solution. The solution is not just to clean the boiler, it's to treat the problem at its source. The plant must install a proper water softening system. This could be a zeolite softener or a demineralization plant to remove the hardness-causing salts before the water ever enters the boiler. All right, let's do a quick recap. 1. Scale is the hard, crusty deposit that acts like an insulator, wasting fuel and making the boiler dangerous. 2. Sludge is the soft, muddy sediment that can clog pipes and valves. 3. Foaming and priming are when impurities create foam that contaminates the steam with water droplets, damaging downstream equipment. And 4. To solve these problems, you must treat the water before it enters the boiler using a water softening process. If this video helped you understand the dangers of hard water in boilers, please hit that like button and subscribe for more simplified engineering videos. Let me know in the comments if you have any questions. Thanks for watching, and I'll see you in the next one.